Okay, so new chapter. In this chapter we are going to develop the system of integers and the system of rational numbers. So in the first section we are going to have a look at integers. Now recall what we did in the second chapter. There we have developed the system of natural numbers. We have proved almost all the basic properties that one can prove in that system. But we have reached the limits of what one can do with only addition and multiplication, and it is high time that we introduce new operation. And the first such new operation is subtraction. However, to define subtraction properly, the system of natural numbers is not enough. We have to make our move to a larger system, the system of integers. Now, informally speaking, an integer is a difference of two natural numbers. Every integer appears in that way. Say for example 2 minus 3 or 1 minus 2 or 5 minus 4 or 5 minus 5. They are integers. We already know about them informally. Okay, we haven't seen a formal development. Now if we follow this pattern and we try to define an integer like this, say we define an integer to be a difference of two natural numbers. Any integer is a difference of two natural numbers. Then it looks fine, but there are three problems with this definition. The first problem is that this definition does not say when two such differences are equal. That is, for example, it does not say why 2 minus 3 is equal to 1 minus 2. Or for that matter, why 2 minus 3 is not equal to 2 minus 4. You have to keep in mind, you may be tempted to say that 2 minus 3 is equal to 1 minus 2 because 2 minus 3 is minus 1, 1 minus 2 is also minus 1. And in that same vein, here the left hand side is minus 1 but the right hand side is minus 2. That may be your answer, but keep in mind we are defining the integers for the first time using the system of natural numbers. We don't know yet that 2 minus 3 is minus 1. We don't even know what minus 1 means. Okay, all we know is that we have natural numbers and we are trying to define integers in this way. Okay, so the first problem is that we need a way to decide when two such differences are equal. The second problem is, of course, the algebraic operations. How do we add two differences? How do we take the product of two such differences? That has to be said. But the third problem is more serious. The third problem involves this expression itself. Note that we are using minus, which is subtraction. Now we have said that we can define subtraction adequately. The operation of subtraction can be adequately defined only after we have defined the system of integers, or at least the set of integers. So if we are using subtraction to define integers and then on that set we are then again defining subtraction, then we are having a sort of, we are trapped in a circularity where we use something and to construct something and then use that constructed thing to define what we started with. That is meaningless. I mean, we have to, it should not be circular. The arguments should go in a tree-like manner. It should never come back. Okay, otherwise the logic is, there is some problem with the logic. Fortunately, the first two problems can be addressed quite easily because we are familiar with integers. We have been using them for so long, although we know about them informally, but our experience with working with integers is so nice that we already know many things about them. So the problem of deciding when two differences are equal can be answered like this. We will say that two differences a minus b and c minus d are equal when and only when a plus d is equal to c plus b. When this happens and only when this happens, we will say that these two differences are equal. And you can see that in this equation, all the things are already available to us in the system of natural numbers. A, B, C, D, these are all natural numbers. Equality of two natural numbers, and this addition is our ordinary addition of natural numbers. So you can interpret this equation by being in the system of natural numbers. You don't need anything new. So we can define equality like this. Same with algebraic operations. We can define this sum to be again such a difference which is a plus c minus b plus d. Note that a and c, b, d, these are all natural. So this a plus c is the ordinary sum of two natural numbers. Same with b plus d. So this is again a natural number minus another natural number. So that's how addition can be defined. And this is coming from our prior knowledge of integers. We already know that this is how things go. Just like that, multiplication can be defined like this. AC plus BD minus AD plus BC. From our previous knowledge of integers, we know that when we multiply two such differences, this is what we get, we should get. So we can define our multiplication like this. And here also you can see that inside the brackets, the operations involved are those in the system of natural numbers and between natural numbers. A, B, C, D, these are all natural numbers. This product is the multiplication we have in the system of natural numbers and the sum of two natural numbers. So in this way we can handle equality and the algebraic operations. However, the problem with this symbol itself persists. What can we do with this minus? Because we don't have minus. So instead of minus, what we will do, we will write a different symbol where we elongate this this horizontal bar somewhat more than what you would write when writing a minus sign, and we consider this symbol as a new type of object. This object has two parts. One part comes to the left of that bar, one part comes to the right of that bar, and both the parts are natural numbers, and such objects we are going to call integers. Then after defining that, on that set we will define equality, addition, multiplication. Okay, and then when the time comes for us to define subtraction, you see, our aim is to be able to define subtraction. So that's why we are doing all these things. So when we define subtraction, eventually we will see that this a minus b actually becomes equal to a minus b, where this will be our newly defined subtraction. So then we can discard this elongated horizontal bar and forget about that. It is there in the definition of integers, but once we do all the things and achieve all the things that we want, we will forget about that and we will continue to use our familiar minus sign. So the role played by this symbol is somewhat like a scaffolding that people use while constructing a building. The scaffolding is there, and then using it one constructs the building. It's there to make sure that the building is constructed properly. But once the building is built, then one dismantles the scaffolding and throws it away and never uses it again. So it will play a similar role here. So let us now go to the actual definition of integers. There are many more things to be said here. We will say them one by one. So this is the first definition. Definition 411, integers. An integer is an expression of the form a dash b. Let us call it that way, a dash b, where a and b are natural numbers. The set of all integers is denoted by z. Okay. Now what is this asterisk doing here? We have something to say about this. We will say it afterwards, but let's just now explore this definition with some examples. Okay. I forgot. I totally forgot. In this definition itself, we also have the criterion for equality. Two integers a dash b and c dash d are considered to be equal, that is, this is equal to c dash d if and only if a plus d is equal to c plus b. So not only have we defined what integers are, but we have also defined when two integers are considered to be equal. The set of all integers is denoted by z. Okay, so we will say something about this expression, but now we are going to look at some examples. Okay, and let me just refill. Thus, for instance, (1-3) is an integer that is equal to 2-4. Because we apply the definition of equality, 1 plus 4 is equal to 2 plus 3. We know that in the system of natural numbers this equation is true. So by definition these two things are equal. These two represent the same integer. Or for instance, 1-3 is not equal to say 5-6 because 1 plus 6 is not equal to 5 plus 3 in the system of natural numbers. So that's how we can decide when two integers are equal. However, despite this nice thing, there is a problem with this, some inconvenience with this notation. We still have some inconvenience with this notation. For instance, 3 is not an integer because 3 is not of the form a-b where a and b are natural numbers. So you see, we already know from our experience with integers that natural numbers themselves are also integers, but we don't see that happening here. This natural number 3 clearly, according to our definition, is not an integer simply because 3 is not of this form. Do you see any dash here? No. Also, in 3 there is only one natural number involved, that is 3 itself. However, according to our definition, an integer must have 2 natural number parts that we don't see here. So what is happening? So definitely something has to be done. Okay, if we just leave this thing like this, then no natural number is an integer, actually, strictly speaking, but we will have to rectify this. We will rectify this later. Okay, that will be taken care of. But now let us come to the expression, use of the word expression here. And this part is going to be somewhat more logical in nature than mathematical. You see, we have really done the following in the above definition. You see, why make matters more complicated when we are getting what we want? I mean, we have got an expression like this and we are calling them integers. Although the expression has some minor inconveniences, we say we will take care of it in future. Okay, but the thing is that from a mathematician's point of view, this is fine, but from a logician's point of view, this is, although it's not something wrong, but it's not satisfactory. You see how we have developed the Zermelo-Fraenkel choice set theory. We have used a set of axioms to define sets and the various operations they have among them. Now, in an axiomatic treatment of something, the aim from a logician's point of view is to simplify the system by using as few axioms as possible. A logician does not want to use many different unrelated things. You see, by that what I mean, if you recall, first we had to postulate that there is an empty set, and then we had to postulate existence of singleton sets, pair sets, etc. Now, in that list of postulates or list of axioms, at one point or another we had to bring in some new objects. For example, while we defined functions, we said that a function is not a set, it's a new type of object that we are introducing into our set theory, which has to behave in so and so ways. That is unsatisfactory from a logician's point of view, because something new has to be brought in. Okay, that cannot be explained with whatever we already have in the system. Functions cannot be satisfactorily explained just using sets. Okay, that point is there. And again, you look at this instance, when we defined the Cartesian product of two sets, then before defining such a Cartesian product, we had to devise the concept of ordered pair of two objects. Now, in the actual definition, we just postulated the existence of such an object which will be called an ordered pair of two objects. where we will have two components, the first coordinate and the second coordinate, which from a logician's point of view is unsatisfactory, because we are bringing something entirely unrelated to whatever we already have in the system from outside. However, later in the exercises we saw that an ordered pair of two objects can actually be defined using only set theory. We don't actually have to postulate its existence. We can define it like this. If you recall, this definition of an ordered pair uses only the elements of set theory, and we don't have to bring in some new object. Now here we are bringing a new object. So from a logician's point of view, this is not satisfactory. So what the logician will do in this case is this. It is somewhat akin to the situation in physics. For example, in particle physics, where we have the theories, quantum mechanics, standard model, all those things now, where there are many things, but there are some fundamental constants like mass of an electron, charge of an electron. Now these values are not predicted by the theory, but they have to be brought in from outside, from the actual physical experiments, and that is unsatisfactory from the point of view of a theoretical physicist. They want to be able to tell about these values or decide these values from the theory itself, which has not been done yet, but that's what they strive for. So a similar situation is arising here. This is like an electron mass which we have just brought in from our experience with the integers. However, using the theory of sets itself, we can make sense of this symbol like this. We have considered the set n cross n, and we have defined an equivalence relation tilt on n cross n by defining two ordered pairs, because the elements in n cross n are ordered pairs of natural numbers, two ordered pairs to be related if and only if a plus d is equal to b plus c or c plus b, same thing. Okay, you can see that instead of writing this symbol, we are writing this symbol, an ordered pair, which is something we already have in our set theory. We don't have to bring in something new from outside. Okay, and this is actually just this equivalence relation is what we have called equality of two integers. You see, actually if you think of it, 1-2 and 2-3, are they really equal without saying anything? No, because you see, this is just like the ordered pair 1, 2, and this is just like the ordered pair 2, 3. We are saying they are equal because something else happens. So this equality is not actually literal equality but an equivalence relation. One can, however, prove that if we define it like this, then it turns out to be an equivalence relation. So according to that equivalence relation, these symbols are considered to be the same thing or represent the same thing, and that same thing is one integer. So strictly speaking, an integer is not just a single symbol but a collection of such symbols, which is nothing but the equivalence class. We then defined A-B to be the equivalence class of all the ordered pairs of natural numbers that are related to A, B. That's what an integer is. If you interpret it strictly using set theory. And in this description, we did not have to use anything, we did not have to bring in something new from outside, like a symbol like this. The symbol itself has found a meaning with only the elements of set theory that we have so far. But there is one thing, a logician would like this, however, this is not so useful for a mathematician, because a mathematician, what he does or what she does is they want to work with these symbols. Okay. However, it just shows that this can be done. It is, the situation is somewhat like defining an ordered pair of two elements. It can be defined using only the elements of set theory. Just like that, an integer can be defined only using the elements of set theory. That's all. So the aim of this footnote, it's actually a footnote in the text, is to show that it can be done in that way. However, we will not interpret integers in this way, because it plays no role in how we manipulate with the integers. Similarly, one can interpret rational numbers later in this chapter and real numbers in the next chapter. Okay. So that's what this thing about expressions. We will continue to think of them as A dash B. Okay. But now we have come to a different type of problem. Fine, we have defined integers as A dash B, A dot B I said, no, A dash B. We have defined integers like that, and we have also defined when we should say that two integers are equal, that is that relation. We have to now prove that that relation is a legitimate relation for equality. We have to now check that our definition of equality of two integers is a legitimate one